cover, I will give the recordings. So then we can almost cover everything. Okay. Now everyone put your main topic as surface tension. Surface tension. Surface tension. Now we might have observed that there are some creatures, very small creatures, move on a surface of water. You might have seen that. Very small creatures, they can walk on the surface of the water. Right, but if we walk on the surface of the sea, but we know that we will definitely we get sink. So then we should understand how some creatures can walk on the surface of liquid. How this happens. And also we might have observed that we might have observed when the beginning, when we opening a tap, when the very beginning, right? When we consider initial drop of that water, initial drop of that water, very careful listen. Now, right now, let's say this is our tap. It's our tap. Now, when the moment we open the tap, at the very beginning, when you consider that first water drop, now you're not opening the tap quickly. If you open the tap slowly, then the initial water droplets, even though that water drop has released, but still it stick with this, still it sticks with this pipe. Because now, if let's this is the mouth of the tap. Now you are gradually turning the what? You are gradually turning the tap. Then you can see that that water drop when you gradually open the tap, that water droplet is building this way, but still that water droplet is stick with the pipe until half of that water droplet sticks the pipe. We can see that this water drop is in contact with the pipe. So therefore, why even we release that water droplet, but why still it builds until it builds completely? Why still it sticks with the pipe? Because of surface tension. That's the idea. So we are talking about what is the surface tension, this property on a liquid surface. So everyone put your main topic as surface tension and write down. Write down. Okay. Right. Certain creatures are seen to walk on water. Write down. Certain creatures are seen to walk on water. Drops of water hang in the form of bags. Drops of water hang in the form of bags from the tap end. From the tap end. From the tap end. From the top. From the tap end prior to dropping out. Prior to dropping out. Prior to dropping out. Continue. When you're writing, understand, write down. A dry steel needle. A dry steel needle. Needle, idikatak. A dry steel needle can be placed smoothly. Can be placed smoothly and made to float on water. Made to float on water. Mercury when spread on a clean glass surface. Mercury, next point. Mercury when spread on a clean glass surface, comma, set in the form of small drops. Set in the form of small drops. Set in the form of small drops. Full stop. These are phenomena we will witness. These are phenomena we will witness in our day-to-day lives. In our day-to-day lives. From these observations, comma, from these observations, comma, it is evident that it is evident that the surface of a liquid behaves the surface of a liquid behaves as a stretched elastic skin. Stretched elastic skin. Highlight the last sentence. Stretched elastic skin. Surface of a liquid behaves as a stretched elastic skin. Now, very important idea, but comparing with other two properties of matter, viscosity and elasticity, surface tension is somewhat complex to understand. But I try maximum to explain all the points, but it's somewhat complex to understand. It's all about explanation, right? If you even I explained, if you could not get the right idea, sometimes you're not able to do the questions. So therefore, very carefully focus until class finishes, right? In case if you notice any connection issues, reply through chat box, right? Okay, okay. Now idea is very clear. Now, sometimes you might have observed that, sometimes you might have seen that. Just take a needle. When we take a needle, if you place this needle gently on the surface of the water, if not some, not all the liquids, if you gently place this needle on top of a liquid, we might have seen that this needle is floating. If not, this needle is floating on the surface of the liquid. Because we know needles are made with metal. Needles are made with metal. So what it should happen? This needle should sink in the liquid, especially in water. But we might have seen that this needle is floating on the surface of the water, right? So and also now this example also very similar understanding. Now when you slowly open the tap, now we expect that water drop, the initially formed water drop, we might expect that as soon as water is formed, we expect it would be fallen down. But for a particular time, now you are gradually open the tap for a particular time until a particular time, this water drop hangs in the tap end. It seems like these liquid surfaces have some kind of uh, stretched surface. It seems like that's the idea. Now I will explain now. The important thing is the conclusion is these examples. We can say that the liquid surfaces act as some kind of stretched elastic skin, rubber balloon. Now the conclusion is how now you know how this rubber balloons stretch. So very similar manner. If I inflate the balloon, we know how it stretches. Very similar manner. Liquid surfaces also act as some kind of surface of rubber balloon. That's the idea. Now put your main topic. Put your main topic. Explanation of surface tension using molecular theory. Explanation of surface tension using molecular theory. Now we are going to explain how this quality, how how these liquid surfaces obtain some kind of elastic property. So we are going to explain that one right now. Okay, right. Give me a second. Right. Now raise your hands. Up to now everything is very clear. Everything is clear up to now. Okay, right. Now your topic is explanation of surface tension using molecular theory. Molecular theory. Then you need to understand now. Now I'm going to explain some kind of important thing. Now there are few keywords you should notice: surface film, sphere of influence, and molecular range. There are some keywords. Molecular range. First of all, you should understand what does it mean by molecular range. Molecular range. Molecular range. Next, you need to understand what does it mean by sphere of influence and surface film. Sphere of influence. Sphere of influence and surface film. Now I take time and explain this idea. Now we know that attraction forces. Now, now gravitational field. Now we learn that between masses there are always attraction forces. So generally we call that gravitational acceleration forces. So very similar manner. So we are discussing about two types of attraction forces. In this chapter, we discuss two types of attraction forces: cohesive forces and adhesive forces. Okay, put your subtopic: cohesive forces and adhesive forces. Cohesive forces and adhesive forces. Subtopic: cohesive, cohesive forces, adhesive forces. Right? Okay. Now write down under cohesive forces. Write down under cohesive forces. Write down the attraction force. Write down the attraction. If I write down the intermolecular force of attraction, the intermolecular forces of attraction between two homogeneous particles. between two homogeneous particles are cohesive forces. Are cohesive forces, right? Then next one is adhesive forces. Write down, write down. The intermolecular forces of attraction between the intermolecular forces of attraction between the intermolecular forces of attraction between two non-homogeneous particles. Two non-homogeneous particles. Non-homogeneous particles are adhesive forces. Adhesive forces. Please highlight cohesive in that under that cohesive forces, intermolecular forces, intermolecular forces, homogeneous, cohesive. In next one, highlight the intermolecular, adhesive, non-homogeneous. Now, this surface tension is a result of cohesive and adhesive forces acting on the particles. Now, what is cohesive forces? Cohesive forces means when you consider two homogeneous particles. For an example, if you consider, let's say now, water is filled in a vessel. Then when I consider the system, I can find out two different particles. I can consider water molecules, water particles. Then I can find vessel. Suppose if the vessel is made with glass particles. When you consider two water particles, they are homogeneous. If you find two water particles in this water, just take water particles, they are homogeneous particles. When you consider glass particles, they are also homogeneous. But when you consider one glass particle and one water particle, they are non-homogeneous particles. That's the idea, right? Then you need to understand always when you consider molecules, there are intermolecular forces. When you consider molecules, there are always attraction forces between on each other. Cohesive forces means when you consider two homogeneous particles, the attraction between those two homogeneous particles we call as cohesive forces. For an example, if water is filled in a glass, the attraction force between two water particles, if not the attraction force between two glass particles, they are cohesive forces. Then what is adhesive forces? In the same example, water is filled in a glass. If I consider water particle and let's say now this water particle is in contact with the glass. If I consider this water particle as glass particle, they are non-homogeneous. Still, there are kind of attraction force between glass particle and water particle. That is what we call as adhesive forces, right? That's very important idea. Now you know what's happening. Now I'm talking about now what's my goal? Surface tension means I explained that all the liquid surfaces they have some kind of they act like some kind of stretch elastic surface. Most of the liquid surfaces they behave like stretched elastic surface. Now I'm going to explain why liquid surfaces act as stretched elastic surfaces. Therefore, this lesson is completely explanation. Therefore, careful listen. If not, you don't understand. I take time and I explain. Right. So whatever, if you feel important, you can write down. Okay. Now I consider a liquid surface. Now very carefully listen. This is very, very important. Very important idea. Now I'm going to explain why they act as some kind of elastic surface, right? I zoom a little bit. Okay. Now it's kind of liquid. It can be water, it can be coconut oil, whatever, some kind of liquid. Then we know that this liquid is filled with liquid particles, liquid molecules. As I mentioned, forget about the boundary, forget about the vessel. If not, just forget about that. Now, think just it's kind of sea. Just think it's kind of sea, right? So we don't consider now kind of liquid is poured in a vessel. In that case, I want to explain adhesive forces as well. First of all, we'll try to understand about these cohesive forces. By understanding cohesive forces, we'll try to understand the reason behind uh, elastic stretch surface of a liquid. Then you know that there are liquid particles only exist. That means we know that when we consider liquid particles, there are intermolecular forces. We call them as cohesive forces, right? Now I consider a particle. Now I consider a liquid particle here. If I consider this liquid particle, now this region is completely filled with that liquid particle. If I consider one particular liquid particle, understand there will be forces acting on this liquid particle by all the liquid particles. Do you understand? Very carefully listen. Let's say now there's a liquid particle here. I use different color. Now there's a liquid particle here. When I consider this liquid particle, there will be cohesive forces acting on this liquid particle by all the liquid particles in this liquid. Particle here also will produce cohesive forces, attraction forces on this liquid particle, right? You understand? Particle somewhere here will also produce intermolecular forces, attraction forces on this considering liquid particle in this way. So likewise, you need to understand all now, the rough understanding is all the liquid particles will produce attraction forces on this particular liquid particle, right? Up to now, everything is very clear. Someone reply, up to now, everything is very good. Just raise your hands if you understood up to now. Just raise your hand. Just raise your hand. Raise your hands if you understood. Right. Okay. Now, now generally understand now. You have an understanding. Just take about this particle as particle 1 and this particle as particle 2. Comparing with particle 1 and no, when you consider particle 1 and 2, the cohesive force produced on this particle by particle 1 is I say F1. The cohesive force on this particle by second particle I say F2. Now which one is large? Now this particle 1 is closer to the considering particle. Particle 2 is far away from the from considering particle. Now which force is large? F1 is larger or F2 is large? Now raise your hands. How many of you say that F1 is large? F1 is large. Raise your hands. F1 is large. F2 is large. F1 is large, right? Because this particle is close to this particle, then we know that attraction force produced by this particle on this black color particle is very high. So therefore, the conclusion is The first conclusion is when you consider a particular particle, all the particles in that liquid will produce attraction forces on that particular particle. And also we know that, and also we know that when the particles are far away from considering particle, the particle that I consider is black color particle. So I can say that the particles which are more away from black color particle, the force, attraction force produced by the particles more away from black color particle is less. Do you understand? So even though this second particle is producing a force on black color one, understand that force on this black color particle is very, 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 very small. So therefore we can neglect. Now if I consider, look here, if I consider this boundary. Now if I consider 3D boundary then, if I take a radius of simple r from the particle I consider, from this black color particle, if I consider radius simple r, if I say beyond this boundary, you should understand this boundary is some kind of sphere. Am I correct? If I take a simple r distance, if I take a simple r distance from this black color particle, that boundary, some kind of sphere. Beyond that sphere, the particles beyond that sphere, the forces created by the particles beyond that sphere on this black color particle is negligible. Even though they create a force, even though the particles beyond the boundaries create some kind of force on the black color particle, you should understand that it they does not make a big impact. Then who is going to make a big impact? Who is going to make a big impact? The particles inside the boundary. The particles inside the boundary. The forces produced by the particles inside the boundary can impact this black color particle, right? So then the conclusion is, I think you understand, then the conclusion is, the conclusion is, conclusion is, conclusion is, very careful listen. Now everything keep in, put in your mind. The conclusion is, I take time to explain. The surface tension is not easy to explain. Not direct theory substitution. Now this is my black color considering liquid particle that is at the center. Then conclusion is, right. Right. Okay. Now I told you there are few points that there are few keywords you should understand. First one is molecular range, then sphere of influence, surface field. Now you will understand that. Now you know what it is coercive and adhesive forces. You have that understanding. And I explained that when you consider the water, when you consider the liquid particle, uh, to that particular liquid particle, all other liquid particles will create forces on that particular liquid particle. But I explained that the particles beyond a particular boundary, the particles beyond a particular boundary, forces created by the particles beyond a particular boundary can be negligible. You understand? The particles, the forces, the attraction forces created by the particles beyond a boundary on that black color particle can be negligible. Then we can understand the particles which is inside the boundary only can impact that considering particle, right? I explained particles beyond the boundary, the impact that particles can make beyond the boundary to this black color particle is negligible, then particles inside the boundary can make some kind of impact on this black color particle, right? I mean, impact in the sense the force. Up to now, everything is very clear. So raise your hands. Up to now, everything is very clear. Everything is very clear, right? Okay. So we are calling. Now. I told you the boundary. How if I consider from this considering particle to a particular distance. If I create a boundary, beyond that boundary, particles cannot make a good impact to this black color particle. In particles inside the boundary can impact this black color particle. That boundary is considered, the boundary is made by creating a distance from the black color particle. So we call that radius of that boundary. This is kind of sphere. We call that radius of that boundary as molecular range. Molecular range. Molecular range, some kind of distance. Molecular range. Right? And what is this sphere of influence? Sphere of influence means, I explained that. I explained that. I just explained some kind of boundary. Beyond that boundary, particles cannot make an impact. Inside that boundary, particles can make an impact. So therefore, that boundary is some kind of sphere. So therefore, that is what we call as sphere of influence. This is what we call a sphere of influence. Sphere of influence. Under the sphere of influence, all the particles are inside the sphere of influence, which can impact the considering particle. Sphere of influence. Sphere of influence. Now I'll ask a question, right? Now I'll ask a question. Now forget about away the boundary. Think about the particles inside the boundary and considering particle black color one. What is the resultant attraction force acting on black color particle? What is the resultant attraction force acting on black color particle? Reply in the chat box. What is the resultant attraction force acting on the black color particle by the particles inside the boundary? Zero. Very good. Because when we consider all the particles inside the boundary, when you consider all the particles inside the boundary, right? Then there are forces acting on black color particle all the directions. But the resultant force, there are forces acting on the black color particle by all these particles, but the resultant force acting on the black color particle is zero. Zero. Right. Zero. Yes, I take time and I explain. It's important. Resultant force acting on black color particle is zero. Right. Okay. Resultant force acting on black color particle is zero. If you take this type of sphere of influence. Resultant force on black particle is zero. Now, up to now, I hope you guys can understand. If I summarize the content is very small thing, but when I explain, I take time to explain. So please draw this. Now take some kind of space here because I'm going to draw very similar diagrams in here as well. First of all, draw this diagram and whatever you feel important, write down. If you finish drawing this one, raise your hands. Then I will start explaining next idea. If you finish drawing this one, raise your hands. Right? Quickly. Finish drawing, raise your hands. Quickly, if you finish drawing, raise your hand. Now, when I explain uh, once again, roughly explain. Now, if I consider a particle, then if I consider this particle, other particles in the fluid create forces on this considering particle, right? But always understand force created on this black color particle by other fluid particles, right? Force created by other fluid particles on this considering particle, generally inversely proportional to inversely proportional to distance to the two particles scared, right? Then you can clearly understand large the distance, force created by other particles on this black color particle is smaller. Large the distance, force created by other particles on this black color particle is smaller. Then we can understand, right? Then we can understand there is a minimum distance. Then we can understand there is a minimum distance because there is a minimum distance. Okay, there is a minimum distance that a particle should locate. See, there should be a minimum distance that a particle should locate it in order to impact this considering particle. Am I correct? Because we can clearly understand when r is larger, the force becomes very smaller. Then in order to impact this black color particle, the minimum distance that a particle should place is we call as molecular range. Molecular range. And if I create a boundary considering molecular range as my distance, if I create a sphere, all the particles inside the sphere I'm calling as sphere of influence. Because if I take the radius as molecular range and if I create a sphere, all the particles inside that sphere is directly impacting this black color particle. But beyond that sphere, particles impact to this black color one is negligible. That is what we call as sphere of influence. And we know if there is a perfect full sphere, you know why the resultant force on this black color particle is zero? Because if you consider this particle, if you consider this particle creates a force vertically upward direction. But the exact opposite direction, there is Same particle in the downward direction is also creating a force on the black color particle downward direction. So therefore, resultant upward and downward cancel out. So very similar, we can assume these particles have spread in this sphere evenly. Therefore, resultant particle on this considering particle, black color particle is zero. That's the idea. Now I'll ask one question. Then this is the sphere for this. This is the sphere of influence for this black color particle. If I consider particle somewhere here, if I consider particle somewhere here, then its sphere of influence will be this way. Am I correct? If I consider this particle, its sphere of influence will be this way. Same R, same R. It should have same R. Sphere of influence. Okay. Okay, same R. Okay. But what would happen? What would happen? Now there is a particle, very carefully listen. If I consider sphere of influence, very carefully listen. If I consider sphere of influence of a particle very closer to the surface of the liquid. Now we know if I consider particle far from the surface of the liquid, resultant force acting on this particle is a zero. Because sphere of influence is a perfect sphere, resultant force acting on this particle is zero. But if I consider particle closer to the surface of the liquid, in that case, it takes time to explain, but you will understand. Whew. Now in this case, now this is, if I consider particle, this is my considering black color particle, then you can clearly see that, sphere of influence is not a perfect sphere. Then reply in the chat box. Now, when you consider particles here, they have a perfect sphere. Ne? So therefore, resultant force acting on this particle is zero. Someone reply, when you consider particles very closer to the surface of the liquid, what would happen? What would happen? You will understand that. You will understand. This sphere is also filled. This is not a perfect sphere, but this region there it is filled with particles. You will understand that. If I mark the forces, you will understand. If I mark the forces, you will understand. You will understand. In this type of cases, when you consider now this particle, you will understand. Do you think resultant force acting on the particles closer to the surface of the liquid is zero? Someone reply. As this particle cannot make a perfect sphere of influence, do you think resultant force acting on these particles will be zero? Reply in chat box. No. Then you will understand The particles closer to the boundary, sorry, the particles close to the surface, the liquid particles closer to the surface has some kind of resultant force acting in downward direction. The resultant intermolecular force. Result intermolecular force, coercive, adhesive, result intermolecular forces acting on the particles closer to the surface of the liquid in downward direction. Am I correct? Right. The particle here, this particle, so half is only half of the sphere of influence is there. In that case, always there in downward direction there is some kind of resultant force. Ne? So this particle has half sphere of influence, half sphere of influence. Then this particle is also having particles on the surface of the liquid is also having some kind of resultant force in downward direction. So therefore, we can say the conclusion. The conclusion is the particles in the range. If you measure the distance from the topmost liquid surface, the particles from the topmost liquid surface to the depth of, if I this is r, depth of 2 capital R, when you consider, very carefully listen, the conclusion is now the radius of the sphere of influence is capital R, molecular length is capital R. If I say that it's twice 2 capital R, the conclusion is the liquid particles from top surface to the 2 capital R depth in the liquid, the particles, when you consider particles in this range, when you consider particles in this range within 2 capital R distance, in this range, these particles undergo some kind of resultant force. These particles undergo some kind of resultant force in downward direction, right? So beyond this limit, there is no resultant force acting on these particles, but particles in the range of 2 capital R from topmost surface, these particles undergo some kind of resultant force in downward direction. So we call this layer the particles which undergo some kind of resultant force in downward direction. This layer, to our layer, we are calling as surface film. This layer is we are calling as surface film. Surface film, right? Now I am talking about because of the characteristic of the surface film. Now you know what is surface film. Now you know how the surface film have formed. Now I'm going to explain because of the characteristic of the surface film of any liquid, how it obtains that stretching ability. Up to now everything is very clear. Raise your hands. Raise your hands. Up to now everything is very clear. Raise your hands. Okay, now write down. We'll draw this diagram. Draw this diagram. This remaining nicely. Draw this diagram. Surface film, mark down surface film to capital R. That idea, everything. If you finish drawing, raise your hands. If you finish drawing, raise your hands. If you finish, raise your hands quickly. Right. Okay. I think time is enough. You'll write down a note. I hope you read the diagram. The tension of a liquid surface can be explained. The tension of a liquid surface can be explained using intermolecular attraction. Using intermolecular attraction. Right? Next point. The molecules in a liquid are attracted. The molecules in a liquid are attracted by the molecules in a liquid are attracted by surrounding molecules. Surrounding molecules. As next point, a sphere be constructed with a molecule. A sphere be constructed with a molecule at its center. At its center, so that it includes so that it includes all other molecules attracting it. All other molecules attracting it. All other molecules attracting it. This sphere is referred to as sphere of influence. This sphere is referred to as sphere of influence. This sphere is referred to as sphere of influence. Red color pen highlights sphere of influence. Sphere of influence. Next point. The sphere of influence of a molecule such as capital E. Now name this molecule as capital E. This molecule as capital E. Write down. The sphere of influence of a molecule such as capital A. Such as capital A. Is situated completely. Is situated completely. Is situated completely inside the liquid. Inside the liquid. Inside the liquid. All molecules in the sphere attracts. All molecules in the sphere attracts. All molecules in the sphere attracts. Okay, right. All molecules in the sphere attracts. Molecule capital A at the center in all directions. Molecule capital A at the center in all directions. Molecule capital A at the center in all directions. Hence, hence, the resultant force on capital A becomes zero. Hence, the resultant force on capital A becomes zero. Resultant force on capital A becomes zero. Next point. However, when considering a molecule such as capital B or C, This is capital B molecule. This is capital C molecule. However, when considering a molecule such as capital B or C, a molecule such as capital B or C, on the liquid surface, on the liquid surface, only the portion of only the portion of the sphere of influence, only the portion of the sphere of influence, only the portion of the sphere of influence is in the liquid, is in the liquid, while upper portion is in the air, while upper portion is in the air. This is the upper portion. While upper portion is in the air, while upper portion is in air. While upper portion is in air. Next point. Since the number of liquid molecules in the lower, since the number of liquid molecules in the lower, since the number of liquid molecules in the lower, since the number of liquid molecules, since the number of liquid molecules in the lower half, lower portion, since the number of liquid molecules in the lower portion is very much larger than, is very much larger than the, is very much large, is very much large, is very much large. Therefore, therefore, a resultant force acts vertical downwards. A resultant force acts vertical downwards. Therefore, a resultant force acts vertical downwards. On each of capital B and C. On each of capital B and C. Next point. This tends the molecules on the liquid surface. This tends the molecules on the liquid surface. This tends the molecules on the liquid surface. This tends the molecules on the liquid surface to move into the liquid. To move into the liquid. To move into the liquid, thereby shrinking the surface, thereby shrinking the surface, thereby shrinking the surface. Hence, hence, the liquid surface behaves as a stretched skin. Hence, The liquid surface behaves as a stretched skin. Hence, the liquid surface behaves as a stretched skin, causing tensional forces to act along it. Causing tensional forces to act along it. Right? Next point. Due to the tendency of molecules to move into the liquid, due to the tendency of molecules to move into the liquid, due to the tendency of molecules to move into the liquid, a small volume of a liquid takes the shape of a sphere. A small volume of a liquid, a small volume of a liquid takes the shape of a sphere, takes the shape of a sphere. Right, now again listen. Again, now this is the only main explanation that I want to tell you. Then remaining is not that much complex. If you understand this idea, then you have some kind of understanding. Give me a second. Uh, right. I will explain further. I will explain further. Okay. I will explain further. Look here. Give me a second. Give me a second. Right. Yes. Now I'll explain. The one last time. Molecular range, sphere of influence, surface field. The one last time. I'll zoom a little bit. So you also draw this diagram roughly. Draw with me. Two times molecular range. Two times molecular range. Molecular range. So then we are calling this as surface film, right? Surface film. Surface film. Then, right. Then we know that when we consider liquid particles in the surface film, if not in between surface of the liquid and the distance 2 into molecular range into the liquid. When we consider these liquid particles, they undergo some kind of resultant force in downward direction. In downward direction. Okay. Some kind of resultant force in downward direction. Now, look here. Now just think that now. Very carefully listen. Just think that now the surface film is completely filled with liquid particles. When you consider those liquid particles, there is some kind of resultant force acting in downward direction. Now just take about a liquid particle somewhere here. If I take a liquid particle somewhere here, very carefully listen. Now if this liquid particle, very carefully listen, if I take this liquid particle just below this boundary, just below this boundary, now let's say this particle needs to move along this thin surface, thin film. This liquid particle needs to move along this thin film in upward direction. Then raise your hands, how many of you say we need to do a work done? This particle needs to do a work done now. We know that. Now entirely this thin film is filled with liquid particles. If these liquid particles moves along this thin film in upward direction, raise your hands, how many of you say that this particle should do some kind of work done? This particle should do some kind of work done. Yes, because we know that these forces, these liquid particles are in downward direction. These forces are in downward direction. These forces acting on the liquid particles are in downward direction. When this particle is moving upwards, we know that this particle should do some kind of work done. Then what would happen for the work done by this particle when moving from here to here? This particle has reached the topmost surface. I'll ask that. Now everything is linked. Don't miss any single point. Everything is linked. When this particle moves just below the boundary and along the thin film in upward direction until its position, this particle has done work done. What happened to that work done? According to conservation of energy, that work done stores as the potential energy of this particle, right? Do you understand? Now, if a new particle coming now, you know why now you might be wondering now why I'm explaining another new particle uh, below a below this surface film. Why I'm explaining when that particle comes to the surface film. Why I'm talking that? You will understand. Surface tension, what we do, we are increasing the surface area of a liquid layer. In surface tension questions, understand. Just think about film created by a soap. Saban Saban වලින් අපි මොකද්ද කියන්නේ soap film. පාටලයක් නේ soap film. So basically what we do in upcoming questions you will understand what we do. We increase the surface area of a liquid. How do we increase surface area of a liquid? When you increase surface area of a liquid, what would happen for the number of liquid molecules on the surface? Increasing, right? Now let's say now, initially, this is your surface area of a liquid. If you are increasing the surface, now this is our boundary. If you are increasing the surface area of a liquid, then how this new surface area has created? By the liquid particles below this surface film. These particles come up. So therefore, that's why I'm explaining what could happen. Everything is important. So I'm explaining what would happen when liquid particle below this surface film moves along this surface film in upward direction. This particle has done work done. That work done is converted. That work done stores as the potential energy of this particle. Right? Okay. That idea is also done. Right? And now, if there's a balloon, when there's a balloon, if I inflate the balloon and if I press the balloon, we can see that that surface of the balloon is going inside. You understand? If there's a balloon, if I just if I just touch that balloon, initial surface was like this. If I touch the balloon, now its surface will be like this. So very similar manner in liquids also. I mentioned that when you consider liquid particles in the surface film, there's result force in down direction. So therefore, when you place something on top of this liquid surface, these particles are ready to go down. Because why? There is result force acting on the particles in down direction. But why they can't go down? Because there are other particles as well in this region. So therefore, these particles want to go down, but these particles can't go down. But these liquid particles are willing to go down one direction, eagerly waiting to go down. Because result force acting down direction, these particles eagerly waiting to go down. So when we place something on top of it, what would happen? These particles go down. When these particles goes down, when these particles go down, now initially the particles which were here have went down. So as a result, still it maintains some kind of surface, and that object, rather than sinking, that object is floating on the surface of that object. Do you understand? Raise your hands up to everything is very clear. If you understood, raise your hands. Right? That's the idea. Okay. So then, next important thing is just think about water surface. Now, you know that when you put a water in in a container, especially just take about small tube, capillary tubes are the best example. If you just take about small tube, and if you put water or mercury or whatever, and when you observe the surface, if it's meniscus, do you think the surface of the water is flat? No, right? We observe that surface of the water, surface of the water has some kind of spherical, curved meniscus, right? If it's a mercury, some kind of spherical surface can be seen in the liquids. Now you want to understand why. That is also because of surface tension, right? Now I explained very carefully. Listen. Now I explained that. Now stability. You know that any object in the universe, all the objects in the universe, they like to be stable. If the objects like if the objects are stable, their energy is minimum. Am I correct? If the object is stable, energy of that object should be minimum. So therefore, all the objects in the universe, they try to reduce its energy and be stable. Very similar manner, I explained. Very similar manner, you know that these particles in the surface film has some kind of potential energy. Am I correct? because when if new layer is formed, if a new layer is formed, I explained that particles in this region will come to this layer by spending work done that stores as potential energy. Then we know that when you consider these particles, they have potential energy. So always this surface film, always the topmost layer wants to be stable. So therefore, always this film, the surface film tries to reduce its potential energy. So someone tell me, how can this surface film, right? If you can reply chat box, reply, how can the surface film reduce its energy, potential energy? Someone reply. Now the surface film needs to be, it should reduce its energy to be stable. How the surface film, that means the particles in the surface film, how surface film reduces its energy? Any idea? It should reduce number of particles in the surface. If the surface contains low number of liquid particles, in that case we can ensure that potential energy on that surface film is low. Then how do we reduce when, if there are low number of particles on the surface, if there are low number of particles on the surface, the surface area should be low. Am I correct? It needs to reduce the number of particles in the surface. When it reduces number of particles in the surface, that surface area will become low. Always understand the low surface, if you want to maintain minimum surface area, then always understand that minimum surface area means always a spherical surface. Do you understand? Under given region, if you want to maintain minimum surface area is always a spherical surface. That's why always liquid surfaces will form some kind of spherical surfaces. Do you understand? Now, because of the spherical surface of the liquid, it's kind of a balloon. If I inflate the balloon, just think about the surface of a balloon. Very similar manner, liquids also, when you zoom it, you will understand the liquids also have some kind of that balloon nature. As their layers, as the topmost surface is spherical shape, it seems like a balloon. So if I apply force on the balloon, we know that what will happen? Its shape changes. Very similar manner, if I apply something on the surface also, the shape changes like a balloon. So therefore, what's happening when the shape changes? There are tension now. We know that when I inflate the balloon, because of its spherical shape, because of spherical shapes, there is tension force on the balloon. Very similar manner, because of the shape of the sphere, because of the shape of that spherical shape of a fluid surface, it is also having some kind of tension, like a balloon. That's what we call a surface tension. Do you understand? Raise your hands up to now, everything is very clear. Raise your hands up to now, everything is very clear. Okay. Now that's the idea. That's the idea. Okay. Right. Then that's done. Now put your main topic, surface tension slash Epsilon coefficient of surface tension. Surface tension slash coefficient of surface tension. Right. Okay. Now what is this coefficient of surface tension? Now we understood somehow, uh, when you consider liquid surfaces, they have some kind of elastic nature. Those liquid surfaces are like stretching surfaces. Now, If I consider a surface, look here. Now I consider liquid surface, understand it's like a balloon surface. And if I draw an imaginary line in some kind of liquid surface, the top view. If I draw an imaginary line having unit length, this imaginary line is having unit length 1 meters. 1 meters, right? Now you know that it's like a balloon surface. How tension force is acting on the balloon surface, because balloon is stretched, right? When we stretch something, tension force is there. Every particle in the balloon surface will undergo some kind of tension force. Very similar manner, every particle in the liquid surface is also undergoing some kind of tension force. So if I draw an imaginary line on the surface of the liquid, tell me, someone tell me, i- if I consider an imaginary line on this liquid, if I draw imaginary line of 1 meter length, someone tell me what is the resultant tension force acting on this imaginary line? Someone reply, what is the resultant tension force acting on this imaginary line? Someone reply, what is the resultant force acting on this imaginary line? Someone reply, what can you say about the resultant tension force acting on this imaginary line of length 1 meters? Just reply your ideas. Reply. Now you are taking a surface, okay? Along the surface, along the surface, along the surface, right? When you consider along the surface, right? Zero, zero. Because along the surface, I don't have a rubber to show that. Rubber, give me a second. Okay, give me a second. As I could not find a rubber. Look here. Now just think about a rubber surface. Now this is your rubber surface. That is stretched rubber surface. If you draw a line, think this is your rubber surface, stretched rubber surface. If you draw an imaginary line, what can you say about the resultant force acting on resultant tension? Because rubber surface is stretched. What can you say about the resultant tension force on this imaginary line? Up and down. If you think it as a single plane, then tension force acting upwards and tension force acting downwards, result will be zero, right? I'm talking a surface, take a surface. But when you consider one direction, if you consider one particular direction, forget about the other direction forces, forget about this direction tension forces. When you consider one direction, then there are tension forces acting on this imaginary line of 1 meter length. But actually, there are tension forces in the opposite direction as well. Now I'm explaining how this surface tension, if not coefficient of surface tension, is defined. It is defined when you consider imaginary line of unit length, that means 1 meter length, the tension forces, the resultant tension force, the resultant tension force acting on that imaginary line in one direction. The resultant tension force acting on this imaginary line in one direction. Because why specifically they mention one direction? The reason is, if you consider all the directions, both the directions, resultant tension force will be zero. Do you understand? That's why they didn't say both directions. They say if you draw an imaginary line on the surface, that is, if you consider imaginary line of unit length on the surface, the resultant tension force acting on that imaginary line in one direction. That is what we call as coefficient of surface tension. I'll draw this diagram and write down. This diagram and write down. Now think this as free liquid surface, topmost surface, free liquid surface, free liquid surface. So write down, write down. We'll take a break at 11. Write down. Uh, the resultant force acting only in one direction. The resultant force acting only in one direction. The resultant force acting only in one direction. Perpendicular to a thin imaginary line. Perpendicular to a thin imaginary line. Perpendicular to a thin imaginary line. 1 meter long. 1 meter long. Drawn on a free liquid surface. Drawn on a free liquid surface. Drawn on a free liquid surface. And tangential to the 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 liquid surface. Highlight resultant force. Highlight resultant force. One direction. Perpendicular. Thin imaginary line. On free liquid surface. On free liquid surface. Tangent. Tangential. Tangential. That's very important. Tangential. Always understand these tension forces are acting on the surface of the liquid. So therefore, these tangential forces are tangent. These tension forces are tangent to the surface. If the surface is flat, very carefully understand. If the surface is flat, then tangential force is also flat. Suppose think if the liquid surface this way. Now because now is your liquid surface. If this is your liquid surface, understand. Now always understand these tension forces are tangential to the liquid surface. Always understand. You will understand. Always understand. These tension forces are tangential to the liquid surface. Right? If the liquid is not flat, if the liquid is flat, tangential forces are also flat. If the liquid surface is not flat in this way, tangential force also in that way. That's the important thing. That's the important thing. Then what is the units of coefficient of surface tension? The unit of coefficient of surface tension? The force, resultant force per unit length. because the idea is resultant tension force per unit length. So therefore, the unit is what? Newton per meter, right? Unit is newtons per meter, and dimensions we can write down dimensions of surface tension coefficient will be if dimension of force over dimension of length MLT minus 2 over capital L. Therefore, I'm getting dimensions of surface tension is MT minus 2, MT minus 2, MT minus 2. Then subtopic surface tension force. Then subtopic surface tension force. Now you can understand what is surface tension force and surface tension. Always understand surface tension, if not surface tension coefficient, is defined for unit length. When you consider unit length, resultant tension force in one direction. When you consider unit length, the resultant tension force in one direction. Then what should be surface tension force? The resultant tension force in one direction for the entire length. For 1 meter length, tension is surface tension coefficient. For the entire length, total surface tension force is how much? If you know capital T, surface tension, if not surface tension coefficient, if you know the total length, capital L, what is the total surface tension force? Capital T into capital L. Write down, write down. If the surface tension force capital F acting, if the surface tension force capital F acting, if the surface tension force capital F acting on a line capital L length, on a line capital L length, on a line capital L length, along the free liquid surface, along the free liquid surface, along the free liquid surface, comma, write on the equation. F equals LT. F equals LT equation. F equals LT equation. I think you guys can understand this idea. Still, we can't do any questions. Still, we have to write in the notes. But the deep this explanation is finished. Now, after we do more theory sections in the surface tension, again, I will go back to the beginning and I will re-explain the same thing quickly once again. Okay. Now again, right. Now understand the surface tension. If not, coefficient of surface tension depends on the liquid. Liquid to liquid, you know that that surface tension acting on the liquid is different. So therefore, surface tension, if not coefficient of surface tension. Give me a second. Give me a second. Right. Then coefficient of surface tension that depends on the liquid. Liquid to liquid, coefficient of surface tension is different. Then next thing is surface tension depends on the temperature. So therefore, write down surface tension, if not coefficient of surface tension, depends on two main factors. Coefficient of surface tension depends on two main factors. Depends on two main factors. Number one, number one, medium in contact with the liquid surface. Number one, number one, we write on the liquid. Sorry, number one, we'll write the liquid. Okay, sorry. Number one, we'll write on the liquid. Number two, we'll write down medium Medium in contact with the liquid surface. Number two, medium in contact with the liquid surface. I will explain. Medium in contact with the liquid surface. Number three, temperature. Number three, temperature. Number three, temperature. Now, generally understand, just think about how surface tension, if not coefficient of surface tension of a liquid varies the temperature. When temperature increases, understand coefficient of surface tension decreases. There is kind of inverse proportionality between coefficient of surface tension and temperature, right? Now, write down topic behavior of surface tension with temperature. Behavior of surface tension with behavior of surface tension with temperature. Under that topic, write down when temperature increases, surface tension decreases. When temperature increases, surface tension decreases. And if I draw the graph, if I draw the graph, y-axis represents surface tension capital T, x-axis represents temperature capital T. Therefore, we have kind of confusion. Therefore, I consider temperature as theta. Then the variation of temperature, variation of surface tension with the temperature will be as below. Draw that graph quickly. Draw that graph. Right. We'll take a break and come. Okay. Now we'll take. The time is exactly 10:45 now. After the break, I explain. We'll take 15-minute break and come. Come at 11. Then continuously I will discuss. Come at 11. Right. Okay. Now we'll write on the new topic. Uh, Free inside the bracket mechanical surface energy. Free inside the bracket mechanical close the bracket surface energy. Right. Under that topic, write down. I will explain. Don't worry. I will explain. Under the topic, write down the amount of work required to increase. The amount of work required to increase the free surface area of a liquid. The amount of work required to increase the free surface area of a liquid by 1 meter squared under isothermal conditions. By 1 meter squared under isothermal condition. Amount of work required to increase the free surface area of a liquid by 1 meter squared under isothermal condition. Okay. Isothermal means write down temperature remains constant. Isothermal means isothermal. Temperature remains constant throughout the process. That's what we call as isothermal, right? Now, what is this free surface energy, free mechanical energy? Now, I explain now. Always understand when you consider liquid surface always wants to maintain minimum energy because liquid surface wants to be stable. Therefore, liquid surface always maintains low energy. Therefore, liquid surface always tries to maintain minimum potential energy. If the liquid surface want to maintain minimum potential energy, it maintains minimum number of possible liquid particles on the surface. it always maintains minimum possible number of liquid particles on the liquid surface. In order to do that, in order to maintain minimum number of liquid particles in the liquid surface, always that liquid surface tries to reduce the surface area of the liquid. Do you understand? Liquid surface wants to be stable, therefore it should reduce its energy, it should reduce its potential energy, therefore it should reduce number of liquid molecules in the surface of the liquid. In order to reduce number of liquid molecules in the surface of the liquid, it should reduce its area as much as possible. So therefore, the possible if now the it should reduce the area as much as possible. Area is minimum if the surface is curved. That's the important thing. Always understand area is minimum. Surface area is minimum if the surface is curved, spherical. That's why always liquid surfaces are spherical, some kind of spherical shape. Now just think that now you might have I don't know what is the word that we call for පොඩි කාලේ අර බැලුන් නෙමෙයි මේ අර සබන් බුබුලු පුම්බන්නේ ගාලා අර පොඩි මේ we might have seen. I can't exactly tell the what is the English word for that. I don't know. Then this is some kind of you put this inside that soap liquid and what you do, you form some kind of soap layer. If not, we call soap film. Then there are soap bubbles. You can create soap bubbles, right? You might have felt that idea. Okay. I thought of not giving recordings. තේරුම් ගන්න recordings දීලා එනොන්ට වැඩේ කරලා දැම්මම හරි. Because I thought I teach my way, right? Recording දෙනවා කියලා කිව්වට recording තමයි බලන්න ඔයා ඉන්නවා උමාර. ඉතින් කටේ නෑනේ. කරන්න ඕනද? And even you unmute, I can't hear you speaking. That's the problem. Because something went wrong with my mic. Okay, just speak, Umar. මං හිතන්නේ something went wrong with my mic. Just speak something. Then I know, right, okay.
Yeah.
Okay, so therefore, this is the problem. They pay the fee. At the end, they don't come. Okay, I don't mind, okay, somehow. Right, we'll talk, we'll do it, okay, right. So then you might have seen that type of device, okay. Then what's happening now? How do you create that soap bubbles? You put this component in that soap liquid. Then what will happen? You can clearly see very thin soap layer, if not very thin soap film, forms on this region. Very thin soap film forms on this region, right? That's the idea. Now we'll assume, look here. Now we'll assume there is a frame, rectangular frame. That's a rectangular frame. We'll assume that if there's a rectangular frame, right? Now just think that we can now, it's a just rectangular frame. That's a rectangular frame. Just assume that we can adjust, we can shift this wire, if not this frame, this length, we can adjust this length. That means we can move this length forward to backward. Just assume now these remaining wires are fixed, but we can move this wire forward to backward direction. Then when we move this wire forward to backward direction, we can adjust the area, right? Adjust the area. Okay. Now just think that suppose if you maintain, now you can move this. Okay, you can move this wire, if not move this rod or whatever, forward or backward direction, right? Let's say if you moved in this in here, if you move this rod or wire here, then this will be the area. Now initially, let's say initially this wire is located in this position, and if you create some kind of soap film, if you create some kind of soap film, then සබන් layer එකක් සබන් මේ පටලයක් soap film is created, in this frame. Okay, this frame, right? Now just think about the surface of this soap film. Now I explained that. Again, I go with the theory that I taught you. Now I explain that. Liquid always wants to be stable. Liquid surface always wants to be stable. Therefore, liquid surface reduces its energy, reduces potential energy, reduces number of liquid molecules as much as possible on the surface. Therefore, in order to reduce number of molecules as much as possible, liquid should maintain low surface area. Low surface area. The surface area low means the minimum low surface area is always a spherical surface area. I told you. Now, just think you have an adjustable frame. That means you can adjust this location of this wire up, forward, or backward direction. By adjusting this wire, you can adjust the area inside this frame. Suppose you think that if you create some kind of soap layer, if you created some kind of soap film. Now, when you are, let's say this soap film is does not break. It even you adjust. Let's assume that even you adjust this wire forward direction, even you move this wire forward direction, that soap film, that soap layer is increasing. The soap film area is increasing. Then now you are moving this wire forward direction. Then you could see that this soap film area, surface area is increasing, right? So initially area, the surface area of the surface film is represented by this black color, so this blue color lines. Suppose if you shifted this wire from this location, now total area of the soap film will be, the total area of the soap film will be this blue color plus this red color area. Then what have you done? Now here somehow when you move the wire, what happens? Somehow surface area of the soap film has increased. If the surface area of the soap film has increased, then you know that more fluid particles, more soap liquid particles has come to the surface film. Am I correct? Do you understand what I'm saying? If the if the if you increase if you move this wire to this position, more soap particles have come to the surface film. That means I told you that when this particle, okay, when these particles come to the surface film, there should be a work done. The particle should do a work done. That work done is converted to some kind of potential in the surface film. You understand? So therefore, understand when we are increasing, if you want to increase the surface area of a liquid, very carefully listen. If the summary is, if we want to increase the surface area of a liquid, the particle should do a work done. How this particle should do a work done? We should give the energy, right? If I'm moving this layer, if I'm moving this wire this side, then we are doing a work done. That work done, because of that work done, particles are moving in the surface film. Do you understand? Right? So then, now what we are doing? Uh, okay. Now we are doing, okay. Uh, right. Now the topic is free surface energy. Free surface energy. Then we wrote that free surface energy as what? Free surface energy means we wrote that resultant force acting only in one direction. Sorry, free surface energy means we wrote that amount of work required to increase the surface area of a liquid by 1 meter square under isostatic condition. Now, in order to increase the surface area of this liquid, we have to do a work done. Amount of work done you have to do in order to increase the surface area by 1 meter square is we call as mechanical surface energy. If you want to increase the surface area by 1 meter square, unit area, Amount of work done you provide is we call as free surface energy, if not mechanical surface energy. Then I can write down, then the symbol of mechanical surface energy is put inside the bracket, write down gamma. The symbol of mechanical surface energy is inside the bracket, put down the symbol is gamma. Gamma. Then I can write down mechanical surface energy. What is gamma? Amount of work done required to increase the surface area by unit 1 meter square. That is equal to total work done, total increase in area. Am I correct? Let's say in order to increase capital A surface area, required work done is W. In order to increase the area by 1 meter square, required work done is we call as gamma. Then W, I can write down A over 1 equals W over gamma. Then gamma equals W over A. Write down these things. Still, we can't do questions. Okay. Now raise your hands up and everything is very clear. Up and everything is very clear. Okay. Then what is the unit of gamma? Unit of work done is Newton meters. Unit of work done is Newton meters. Unit of work done is Newton meters. Unit of area is meter squared. Gamma means Newton per meter. What is the dimension of gamma? Dimension of work done over dimension of area. Dimension of work done means we know that ml square t minus 2. Dimension of area is L squared. We will get that dimension of surface tension is m t to the power minus 2. M t to the power minus 2. Write on them. Okay. Now the conclusion. Okay, now again I will come up with the conclusion. Even though we take this much of time and even I explain everything, if I don't explain that way, sometimes you are not able to understand the idea behind the surface tension. Now, surface tension means some kind of elastic, some kind of stretched, elastic nature of liquid surfaces, like balloon surfaces, right? Surface tension means some kind of stretched, elastic nature of liquid surfaces, like balloon surfaces. And then you should understand how it is formed. It is formed how I explained, but I don't explain it again, right? But always understand all the liquid surfaces want to be stable. Therefore, liquid surfaces reduce the energy as much as possible. Therefore, they reduce potential energy as much as possible by reducing number of liquid molecules in the surface. How do they reduce number of some kind of curved surface area? That's the important thing. Next important thing you should understand is what is the surface tension? If not, what is this coefficient of surface tension? You should understand what is surface tension. If not, what is this coefficient of surface tension? That's very, very important. Now, how did we define surface tension? Surface tension means you know that when we consider free liquid surface, if you consider one imaginary line within unit length, when you consider unit length of imaginary line, resultant tension force per unit length. You can say that way. Resultant tension force per unit length. That's what we call as surface tension. How we define this mechanical, what free mechanical energy? How we defined free surface energy? Free surface energy means work done per unit area. In order to increase the surface area of a liquid by 1 meter square, required work done is we defined as free surface energy. What is surface tension? Surface tension means uh, resultant force per unit length. What is free surface energy? Work done per unit area. Now we are going to prove that surface tension, capital Tn, gamma are equal, right? Now topic proving that capital T equals gamma, proving that capital T equals gamma, proving that capital T equals gamma. After this, we can do some questions. Now draw this diagram with me. This diagram with me. Start draw this diagram with me. I'm going to prove that capital T equals gamma. Now, as I mentioned before, this PQ uh, length different wire can be adjusted, can be moved. Then now look here, this is some kind of frame. Now this is some kind of frame. Then I explained that now some kind of soap layer, soap film is maintained in this region. Okay. Then if I draw an imaginary line, very carefully listen. If I draw an imaginary line here, then the resultant tension force will be zero, right? If I draw imaginary line here, resultant tension force will be zero. What can we say about now? This layer, this liquid layer is in contact with these boundaries. This layer is in contact with these wire. This layer is in contact with these wires. You need to understand there are surface tension forces acting on these wires. But you should understand these wires are fixed wires. Am I correct? Surface tension forces are perpendicular to the along the surface, tangential to the surface, like this. Very similar manner, these surface tension forces are acting on this PQ wire as well. Am I correct? Why? Because if you consider any line, if you consider any line in the fluid, then tension force acting in both the directions, therefore resultant is zero. But when you consider this line, if you draw a line here, if you draw a line which lies along these wires, then the fluid is only in one side. So therefore there is some kind of resultant tension force. But as these wires are fixed in these regions, we don't think about surface tension forces. Because why? Because these wires are fixed. Therefore, we don't discuss surface tension on these wires. I hope you understand what I'm saying. But we are going to move this PQ wire. Therefore, we only mark tension forces. That means surface tension forces only on this wire PQ. This wire PQ, right? Keep on drawing this diagram. You draw the diagram, right? Now, now you understand. Along this PQ wire, there are surface tension forces acting on this PQ wire in left side direction. If I take the resultant tension force at, let's say, length of PQ wire. If I say length of PQ wire is capital L, length of PQ wire is capital L, the resultant, if I say surface tension, coefficient of surface tension, if not surface tension is capital T, if I say length of the PQ wire is capital L, then resultant tension force acting on PQ wire is, I say that, what? It will be capital F. I say capital F. Resultant tension force acting on PQ wire is capital F. If I say surface tension is capital T, then you should understand capital F equals T into capital L. I explain. Surface tension force, capital F equals surface tension capital T into capital L. You know why? I explained before. Now, what's my goal is, now I want to increase the surface area of this soap film. If I want to increase the surface area of the soap film, then you know that I have to provide the work done, because I want to drag this PQ wire this direction. I want to drag this PQ wire in this direction. When I am dragging PQ wire this direction, I need to provide a force on PQ wire at least equal to capital F. Do you understand? I should provide a force PQ wire at least equal to capital F, right? Then let's say the force provided by myself is also equals to capital F, capital F. Then I increased, understand, then I increased surface area. I applied F dash force at least equal to capital F and I increased the surface area. I moved this PQ wire to this P dash Q dash position. I say this gap is simple X. This gap is simple X. I move this PQ wire to a distance simple x. Then if I ask you what is my total surface area of the soap film, this blue color area plus this area, x into capital L, x into capital L. Now I can write, now what's my goal? I'm going to prove that this T equals gamma. Then I can say that, I can write down, uh, I can write down the total surface tension force, total surface tension force, total surface tension force on PQY, that is equals to F dash. We know F dash is equals to capital F. Capital F means if I say surface tension is capital T, F dash I can write on F means length into capital T, right? F means F dash means F means L into capital T. Raise your hands up to everything is very clear. Raise your hands up to everything is very clear. Now the confusing point start because the thing is now up to now everything is very clear. Now normally understand now for a soap layer, only for soap layer, understand soap layers have two layers. This soap film, I think I don't know how many of you can understand now. For me also it's really confusing. In now when you consider any other liquid, normally they have only one surface, right? When you consider any liquid, they have only one surface. So therefore, if you want to for now this PQ wire is touching that surface. So therefore, if you want to find the force acting on that PQ wire, there is only one surface. Therefore, we can say tension force capital T into L. But normally we say that soap layers contain two layers. If you maintain a soap film, understand, soap film contains two layers, topmost layer and bottommost layer. Soap film, I don't know how many of you can understand now, roughly understand now this soap. If I draw the 3D view of this PQ wire, look here, if I draw the 3D view of this PQ wire, okay, soap layers, there are two soap layers. There are two, when you consider soap film, there are two surfaces of a soap film. Topmost surface, topmost surface of the soap layer. In that soap film, there are two layers of soap. Topmost layer, because of this topmost layer in contact with the PQ, there are tension forces LT. LT. And also there is another bottom layer in soap film. There is another bottom layer in soap film. Bottom layer in soap film. Because of that bottom layer, understand, again, bottom layer is also in contact with the PQ rod. Therefore, understand, again, there will be a resultant force LT. Then if I ask you, F dash equals F means L into capital T into 2. The most people does not understand why it is 2. The reason how I justify why it is to understand, if especially soap film contains two layers. Topmost layer is also in contact with the PQ wire. Bottommost layer also in contact with the PQ wire. As a result, there will be two surface tension forces acting on the wire, LT, LT. So therefore, resultant surface tension force is LT into 2. Did you understand? Raise your hands, how many of you, this part is really confusing part. Raise your hands, how many of you understand what I'm saying? Understood? Okay. So then that's why I multiply by 2. Okay. Then that is done, right? Then I can write down. You also keep on writing. I can write down. If you see write down as there are two layers. There are two surfaces. There are two surfaces in a soap film. In a soap film. That's why we multiply by 2. If there is only one layer, we just multiply by 1, right? Now in order to move, right? Okay, sorry. In order to move this PQ wire, we have to provide a force capital F dash that is at least equal to capital F, right? Okay. Minimum force required. We know F dash is, we know that F dash is at least equal to capital F. That is also, that means 2LT. 2LT equation 1. Now, because of this capital F dash force, the work done. Because of this capital F dash force, the work done. The work done due to capital F dash force equals to what? We know the equation for work done, W equals force into displacement. Force is F dash. I say W1 work done. Force is F dash into displacement is simple X. This PQ has moved here. Work done means force into displacement, F dash into simple X. Then I can write down W1 equals F dash. F dash equals 2LT simple X. This will be my equation 2. Right? Equation 2. And also we know that work done, why the amount of work done is converted to increase the area of the surface. Then how do we find the work done required to increase the area? What is the increased area? Increased area will be L into X, right? This is here this is W1 equals 2LTX, okay, equation 2. Now increased area. Increased surface area is L into simple X into 2. Why? Because as I mentioned, this soap film has 2 layers. Then topmost layer area also increased, bottommost layer area also increased. Therefore, increased area means is the increased area. So then L into X, there are 2 layers. Topmost layer increased area is Lx, bottommost layer increased area is also Lx. Therefore, 2 Lx. Then I can find when area is increased by this much, the required work done. I can write down required work done. Required work done. I say W2. That is equal to how much? Gamma. Gamma means required work done to increase the area by 1 meter square. Gamma means required work done to increase the area by 1 meter square. Now this much area is increased. Therefore, gamma into Lx into 2. Equation 3. I know that W2 and W1 must be equal. Whatever the work done that we do, that work done is used to increase the area by this much. Therefore, I can say W1 equals W2. Therefore, I can say 2L capital T X equals gamma Lx into 2. 2 cancel out. Lx cancel out. Therefore, I can say T equals gamma. Did you understand? Raise your hands if you understood. Raise your hands. If you understood, raise your hands. It's very then hereafter. It's not difficult. Hereafter, it's easy. Now start writing. If you finish writing, raise your hands. If you finish writing, raise your hands. Then difficult part is done. Then hereafter, we can do the easy part.
If you finish, raise your hands. If you finish, raise your hands. Right. Now we'll do a question. I will send a picture of that question in the group. Uh, mm, mm, as I sent. Now, question number one. Start doing question number one quickly. Liquid film of surface tension this much, capital T 7 into 10 to the power minus 2, form between two parallel wires of length 10 centimeter, placed at a distance 0.5 centimeter far from each other. Right? Parallel wires. Length of the wire is 10 centimeters. The gap between the two wires is 0.5 centimeter. Find the work required to double the distance between two wires under isothermal conditions. Start doing that question quickly. If you now you can do it now. The very easy idea. Work done, required work done means now you know that. Find the area, find the increase area. Very carefully listen. Always now. The idea is very simple. If there's a liquid surface, in order to increase the surface area of the liquid, we need to do a work done. Do you understand? The amount of work done that we do equals always gamma into capital A. Gamma into capital A. Do you understand? If not, gamma means capital T, therefore capital T into capital A. Amount of work done that we do. Understand, if they mention it is soap liquid, then always understand soap liquid has two layers. Always multiply by two. Always the area multiply by two. Other than if you just mention liquids, only just multiply by one. Only just take the area. That's the idea. If you got the answer, put the answer in the chat box quickly. Quickly. Now you can do it. It's not difficult now. Now we can do the questions. Sorry. Ah, Anyone got the answer? If you got the answers, put the answers in the chat box. And start doing second question also. Start doing second question also. Start doing second question also quickly. Start doing second question also quickly. Quickly. Now second one is also not that much difficult. Now second one they say that find the amount of work required to break a small liquid droplet of radius capital R into 8 droplets under isothermal condition made of liquid of surface tension capital T. Now find the surface area before and after. Find the surface area before and after. Now this larger one is going to break into small 8 small spheres. Find before surface area and after surface area. First of all, do that. Now they have given the required to break a small liquid droplet of radius capital R into 8 droplets under isothermal condition. Uh, now this one having a radius capital R, surface tension capital T, we are going to break into 8 small spheres. Let's say this radius is simple R. Simple R. Now try to find the surface area of this entire small spheres and try to find the surface area of this large sphere. First of all, do that. Quickly. Give me a second. Look here. Now I will do second case. I will do second one for your understanding. Look here. I will do that second question. Very carefully listen what's happening. Uh, now we are going to break a liquid. There is a liquid droplet of radius capital R. Amount of work required to break a small liquid droplet of radius capital R into 8 droplets. Look here very carefully. Now let's say now there is a liquid droplet of radius capital R. Surface tension capital T. Okay, surface tension of this fluid, this liquid is capital T. Then I'm going to break this liquid droplet of radius capital R into 8 small spherical droplets. 8 small spherical droplets, right? Just assume radius of this small spherical droplet is simple R. Simple R. I don't know exactly. But you know that the total mass, the mass of this large spherical droplet 10, the mass of small spherical 8 droplet will be same, because this droplet is divided into 8 small droplets. Therefore, total mass of this large droplet 10, total mass of these 8 droplets must be same. That idea, I think you can understand. Now, let's say now both of them are same liquid. Therefore, density I say rho. Both of them have same density rho. Then I can say I can find the mass of this droplet. Mass means we know that volume into density. Mass means we know that volume into density, right? Now, volume. I say this mass is m1. M1, I can say that volume means a sphere. 4/3 phi capital R cube. Density is rho. Then mass of this small sphere, if I say M2, M2 will be 4/3 phi R cube. 4/3 phi R cube. Density is rho. Then I know this is the mass of the larger droplet, mass of the smaller droplet. Then I can write down M1 equals 8 times M2. M1 equals 8 times M2. Am I correct? M1 means 4/3 phi capital R cube, density rho. What is M2? 8 into 4/3 phi R cube, density rho. Rho cancel out. Then I can write down 4/3 phi R cube. 4/3 phi cancel out. Then I am getting that R cube equals 8. R cube equals 8. Simple R cube. Then I can write down simple R in terms of capital R. Then I can say simple R equals how much? This is 8 means 2 to the power 3. 8 means I know that 2 to the power 3. I can write down R cube over 2 to the power 3 equals simple R cube. Simple R cube. Therefore, I can subtract the radius of smaller sphere. Simple R equals R over 2. But this is not we want to find. Up to everything is very clear. Raise your hands. Up to everything is very clear. Up to everything is very clear. Raise your hands. Right. Okay. But we need to find the question. We need to find amount of work required to break a small liquid droplet of radius capital R into 8 droplets and the amount of work done. Now, shall we find the surface area? If we find the surface area, now, if I find the surface area, the equation to find surface area of a sphere is 4 phi r squared. Surface area equation is 4 phi r squared. Surface area equation, capital A equals 4 phi r squared. 4 phi r squared. If I find the surface area of this large droplet 10, if I find the total surface area of all 8 small droplets, if I find them, I say A1, this is A2, A1, A2, A1, A2. So next time when I do the class, I will again summarizing and I explain next important things. Then today it seemed like very unfamiliar, but next year when I do this again, you will be very familiar. Then I can say that A1 equals 4 phi capital R squared. What is my A2? The total is my A2. Okay, total is my A2. A2 equals 8 into 4 phi simple R squared. R is R over 2. R squared over 4. then I can say that A2 will be 2. If I cut this one, 2 into 8, 2 into 4 means 85 r square. Then what happened? When this large droplet breaks into 8 smaller droplets, what happened to the surface area of the droplets? That liquid, surface area of the liquid has increased. In that case, work has to be done. If the surface area has increased, how surface area can increase other than if you don't provide a force, if you don't provide a work done. Unless we don't provide a work done, surface area of the particles cannot be increased. So therefore, what is the increased surface area? Increased surface area will be 85 r squared minus 45 r squared. Therefore, increased surface area will be just 45 r squared. Now we need to find the work done. Now work done means gamma into capital A. Work done means gamma into capital A. I told that gamma means capital T into capital E. Okay, because gamma equals T. Therefore, I can write down required work done equals capital T. Area is 45 r square. Did you understand? Raise your hands if you understood the question. Raise your hands. If you understood, raise your hands quickly. Either you can't see it down. Now then, W equals capital T into A means 45 r square. Now write down that question and quickly do it. Question number 3. Question number 3. Start doing third question. Raise your hands. How many of you started doing third one answer? How many of you started doing third one answer? Yes. Initially, it seems like complex idea, but the application is very simple, but understanding is somewhat complex. Pay attention. Raise your hands, finish doing third one. If I do third one, uh, right, says that, okay, find the amount of work required to break a drop of radius 0.5 centimeter into droplets of radius 1 millimeter under isothermal conditions, surface this much. Find amount of work required to break a drop of radius this much into droplets of radius 1 millimeter. Oh, same idea. Oh, same idea. This time, okay. Question number 3. The same idea. It says that amount of work required to break a drop of radius cap 0.5 centimeter into 1 millimeter. I don't know how many number of droplets. Simple in I say simple number of droplets. Capital R I say 0.5 centimeters. Simple R I say 1 millimeter. 1 millimeter. I can break into simple number of droplets. I can break into simple number of droplets. We'll think that way. Simple number of droplets. Okay. Simple R, I know simple R and capital R. Capital R is how much? 0.5 centimeters. That means 5 into 10 to the power minus 3 meters. Simple R means 0.1 millimeters. Sorry, 1 millimeters. That means 10 to the power minus 3. 10 to the power minus 3 meters. Then same idea. The mass same. Mass before and after same. Therefore, I can say this one's mass is 4 over 3 phi r cube. 4 over 3 phi r cube rho should be equal to simple n into 4 over 3 phi simple r cube density rho. Then rho cancel out, 4 over 3 phi cancel out. I'm getting simple n will be capital R cube over simple R cube. Capital R cube over simple R cube. Capital R means we can write down phi minus 3 cube over minus 3 cube. So therefore I'm getting minus 3 cancel out. Then I'm getting here phi cube. Am I correct? That means 125. I can divide into 125 number of small droplets of radius 1 millimeter. But they are asking the work done area. They are asking the work done before area and after area. Before area, if I say before area A1, before area will be 4 phi capital R squared. After area will be A2. My A2 will be simple n into 4 phi simple R squared. Now simplify this. If you simplify this, then problem solved. Okay. Now change in area delta A. Change in area will be now. Which one is larger? Which one is larger? We'll assume this one is larger. If we assume this one is larger, but we can exactly tell which one is larger. You can find this one. 4, 5. Okay, we'll find the area first and we'll get the change in area. Here 4, 3.14, 3.14. R means 5 minus 3 whole square. 5 minus 3 whole square. Then I am getting A1 equals 4 into 3.14, 25 minus 6. If you simplify, what will you get? 100, 3.14 means 314. 3.14 10 to the power minus 4 meters square. If I find A2, 125, 4 into 3.14 into R means minus 3, minus 6. 125 into 4 means 500. Nee, 500. 500 into 3.4 means 314 into 5. 314 into 5 means how much? 715. 1570. 1570. 1515.70 10 to the power minus 4 meter square. Then this one is large. Change in area. Delta A will be 15.7 minus 3.14 minus 4. Then 15.7, 3.14, 6, 5, 2, 10, 7, 5, 1. 12.56 minus 4 multiply by capital T. Did you understand? Raise your hands if you understood question number 3. Raise your hands. If you understood question number, raise your hands. Okay. Then that is also done. Uh, okay, we'll do 1, 2, 3 done. Let's start doing question number 4 and 5. Start doing question number 4 and 5. We'll do question number 4 and 5. Question number 4 and 5. Start doing question number 4 and 5. Start doing fourth one, fifth one. Done. Question number 4 finished, raise your hands. Fourth one finished. Fourth one finished, raise your hands. Very similar idea. I think fourth one, if you do it, the answer would be answer for question number 4 will be 2.12 10 to the power minus 10 joules. 2.12 10 to the power minus 10 joules. 2.1 to the power minus 10 joules. Raise your hands. Anyone got at least this value roughly? Then okay, roughly okay, 2 point something minus 10 is there. Then when you do simplification, small mistakes. Okay, I think because of that, I think. Now next question. Now next one is that's a good question. Now question number 5, I will do question number 5. That you can also do it. You can also do it. I will do question number 5. It says that uh, mm, soap bubble of radius 3 centimeters and another soap bubble of radius 4 centimeter inflated with the same soap solution collide with each other under isothermal condition to form large bubble. Find the radius of the large bubble. Find the radius of the large bubble. Now there are two bubbles. Now I told you when it comes to soap bubbles, do you understand? When it comes to soap bubbles, understand there are two layers. Two layers. Now let's say now, okay. There are two soap bubbles, they merge together and they combine together and form larger bubble, right? This one is having simple R1 radius, R1. This bubble is having, I say simple R2. When they combine, the result would be a large bubble. I say this is capital R, capital R. So then if I ask you what is the surface area of this soap bubble of R1 radius, so most of you might tell that 4 5 R1 square. That's wrong. 2 into 4 5 R square. Because I mentioned soap bubbles have two areas. 2 into 4 5 R1 square plus 2 into 4 5 R2 squared equals 2 into 4 5 capital R square. Then all these two terms cancel out. 4 5 4 5 4 5 cancel out. I am getting here R1 squared plus R2 squared equals capital R squared. So then you can easily find the answer. This is, I think, 3 centimeters, 4 centimeters radius. Yeah, radius are 3 and 4. Then 3 squared plus 4 squared equals R squared. Then R will be 5 centimeters. R will be 5 centimeters. That's the idea. Did you understand? Now raise your hands. Whatever we learned up to now, everything is very clear. Now, if you properly listen to what I explained, because I took time and I explained because it's somewhat complex part. Then important section is finished, but still we have to do some important things. Right. Mm. After I finish surface tension, I will do this thermo, that heat small thing is pending. Then I will go to that electronics. I will give the unit 3 recordings. And in that way, we have to finish. Okay. Now, okay. Now I will stop for now. I will stop the class now. Morning time, if students they don't come, then I will put the class in the night, 8 p.m. to 11:30. I will put the class in that way, right? So therefore now one day I will take one day within, I don't know, tomorrow night or maybe mostly tomorrow night. Then I don't do tomorrow morning. Then I will do in the night. Tomorrow night I will do one class and I will complete surface tension. Then again next week, if not Saturday or Sunday, I have no idea. Then somehow November I will finish everything. I will put classes and November I'll finish everything. Okay. So then I think the most important thing is done. Then still I have to teach you some important things. We'll do on next day, mostly on tomorrow night. Okay, we'll stop the class for today.